very much. Okay, great. So thank you for joining us today. My name is Bese and I work at Brighter Spark. And welcome to today's Spark Talk, which is a crash course in good and bad controls with Carlos Cinelli. I'd like us to begin by giving honor and thanks to the Hode, Osoni, and Anishinaabe nations as the traditional inhabitants of the lands where McMaster stands. To say that is to acknowledge a debt to those who were here before us and to recognize our responsibility as guests, to respect and honor the intimate relationship Indigenous peoples have to this land. Carlos Cinelli is an assistant professor at the Department of Statistics at the University of Washington, and his research focuses on developing new causal and statistical methods for transparent and robust causal claims in the empirical sciences. So thank you so much, Carlos, for joining us today, and I'll hand it over to you.
Thank you. Thank you, everyone. It's a great pleasure to be here. What has been said, I'm Carlos Cinelli. I'm an assistant professor at the University of Washington. And today we're going to be talking about good and bad controls in regression. So what covariates should you be including in your regression equation to estimate causal effects? And this is, let me just see if my mouse is working. Okay. And this talk is based on this paper jointly with Andrew Forney, and the paper has been published already, although I actually suggest you read the preprint version, which is better, well formatted than the journal version, but up to you. So if you are like in the social or health sciences or the empirical sciences in general, and you're in a seminar, or if you submitted your paper to a journal, which is an empirical paper using correlation, but it's trying to make some causal claims, the first thing that you probably heard someone ask you is, have you controlled for, right? Many, if not most studies in empirical sciences aim to identify a causal effect, even if the study tries to couch that with correlational language and say, I'm not trying to identify causation, I'm just doing correlation. But then when you see the reasons why the study justifies the importance of the research question, these are causal questions, or when the study goes to discuss policy implications, these are causal questions, and so on. Even if implicitly, and if the study is swearing that they're not trying to do causation, most of the time they are. And here's just one example from Twitter in 2019. So this was a tweet that went viral. The New York Times tweeted that, do you want to live longer? Try going to the opera. Researchers in Britain have found that people who reported going to a museum or concert even once a year lived longer than those who didn't, right? And then, of course, the study is going to be saying that this is not causal, this is just correlation. But then when you look at the implications, also, we probably should be going more to the opera. So if you should probably be going more to the opera, that's you're trying to draw causal effects from these associations. But we all should know, at least you have been told, that association is not causation, and observation studies are always under the threat of unobserved confounders. The first thing that many applied researchers learn in a traditional statistics or econometrics course is that you should add controls to your regression equation in order to avoid omitted variable bias. So for example, in the study above, so this is not working as intended. Okay. I'm going to use it here. So the study above, so people were discussing the study on Twitter and saying, oh, I know what the confounder is. If you're filthy rich, you go more to the opera. And if you're filthy rich, you have a better health. But of course, for example, in this case, this study did control for socioeconomic factors like income, educational level, and other things, right? So the first thing you learn as an empirical researcher is to add things to your regression equation. So if that's all the training you had, you may be left under the impression that you should always control for everything. So the more, the merrier. But not all controls are created equal. So it has been known for a long time, even though it's not as known among practitioners, but this is changing now, that some variables, when added to the regression equation, can in fact increase bias. And such variables now have become known as bad controls, at least in the econometrics literature. And the typical warning you would find in textbooks is that bad control, so these variables that you should not put in a regression equation, are variables that could be quote unquote affected by the treatment. So these are post-treatment variables. And this is the typical warning you would find. So this is in a famous econometrics textbook called Mostly Harmless Econometrics. Some variables are bad controls and should not be included in a regression model, even when their inclusion might be expected to change the Sharpe regression coefficients. Bad controls are variables that are themselves outcome variables in the notional experiment at hand. So the idea is, if you could imagine that the treatment of interest could have affected that variable, so this is something that is a potential effect of your treatment, then you should not put that in a regression equation. So this is an improvement. Okay, this rule of thumb can help you avoid some egregious errors. But it turns out that this is neither necessary nor sufficient for deciding whether a variable is a good or bad control. Okay, so what can we do now? So it turns out that we have a lot of tools that can help us make a more disciplined conversation about which variables we should control and which variables should not control. And this is using graphical models. So recent advances in graphical models have produced simple criteria to distinguish good from bad controls. So what do I mean by that? So this criteria allows us to, number one, decide which variables should be included in the regression equation in order to identify the causal effect of interest. So you tell me, I want to identify the total effect of X on Y, then we can tell, then you should adjust for this, you should not adjust for that, and so on. And not only that, it helps us decide among a set of value adjustment sets, which variables would yield more precise estimates. So the first question is concerned only with asymptotic bias, which would be what we call identification. The second one is saying sometimes, even if two different sets of variables allows you to identify the cause effect, some of them may be better for precision in finite samples. So you're going to get smaller standard errors. So which of those variables should we pick? And our goal today is going to be to practice these main lessons that graphical models offer through simple examples. And why I'm saying that? Because in theory, I could just state you one or two theorems, and that would be it. So basically, I can summarize this criterion with one or two main results. They would be stated in terms of graph language, and you would be done. But in practice, we'll realize that it's not like you learn a theorem and you internalize the concept. It is actually very helpful to go through several examples to really internalize the logic, right? So what we're going to focus here is the logic. And then if after going through the whole lecture, and then you can read the paper again, and then if you go to the appendix of the paper, which I actually highly recommend, then you can read the theorems and see, oh, now I understand why the theorem is stated in this way, right? So my goal here, hopefully, is to show you that causal diagrams can help make otherwise difficult problems very easy to solve by literally a simple inspection of the diagram. So everything that I'm going to show you here is formal in the sense that behind it, we would be manipulating non-parametric structure equation models to derive the answer that I'm going to tell you what the answer is. But instead of having to do this derivation by hand, doing calculations with equations, it could be linear, it could be non-parametric, almost everything I'm going to tell you here is non-parametric. Instead of doing these manipulations, what we can see is that we can just look at the graph, see some patterns in the graph, and then decide. And that is it, formally equivalent to a derivation. Okay? So it's not just an intuition or just an illustration. It's actually a calculation that you're doing by using the diagram as an auxiliary tool. Okay, and then just to motivate, because after this, I'm going to just be talking about graphs, and I'm not going to be too worried about giving real examples. So it'll be like when you're practicing calculus, and then you say, let's practice the chain rule, and let's practice the multiplication rule. So we're going to be focused on very simple examples. And so you may be wondering, is this useful or is this not useful? So before going there, I want to give you two real-world research paradoxes that the tools that I'm going to show you are going to help you quickly understand and perhaps solve these paradoxes. So I'm going to show you here, then we're going to go through a bunch of examples in graphs, then I'm going to come back to this paradox. So the first one is the birth weight paradox. So this is a famous paradox in epidemiology, and this shows up every time in several different forms, okay? not just in the birth weight. So the latest one I saw on the internet was Alzheimer and smoking, actually, which is basically has the same structure of this paradox. And then some people saying, oh, could smoking prevent Alzheimer's and so on. So this one is what epidemiologists found in the data was that infants born to smokers, to mothers who smoke, were found to have higher risks of mortality than than infants born to mothers that do not smoke. Okay, so far this makes sense, right? So you'd imagine that smoking is bad. So if the mother smokes, you would imagine the babies would have higher risk of mortality. However, among infants with low birth weight, this relationship was reversed. So what does that mean? So when I just stratified the data and I just picked low birth weight infants, and then I looked the low birth weight infants born to mothers who smoke, they were found to have lower risk of mortality than infants born to mothers that do smoke. So this reversal effect has created many controversies in epidemiology. So for example, does it mean that maternal smoking is beneficial for low birth weight infants? And if you think, oh, no, probably not, right? That's not enough. Just saying probably not. You probably should try to explain, okay, but how could I see this association in the data, even if smoking was not protective? Oh, sorry, low birth weight smoking was not protective for low birth weight infants, right? So how could I see this in the data? How can I explain that? So think about it a little bit, and if it's not easy to you to come up with an answer, that's good. You're going to learn something in this talk. The other one is the antebellum puzzle. So this is from economic history. So this interesting puzzle in economic history is the fact that during the 19th century in Britain and the United States, some of the records we have shows that the average height of adult men fell, even though economic conditions of these countries improved alongside with childhood nutrition. So imagine that economic conditions are improving, childhood nutrition will be improving. So we'd expect to see the average height increasing as well, but that's not on the data that we have. So why is that? Does that mean that nutrition reduced the heights of adult men? Then most likely you'll say, oh, of course not. There's something else going on here. What could it be? So what is happening here? So these are all related to back controls in a way, in another. And then hopefully by the end of the talk, it will be easier for us to do two things. One, we're going to have a language to easily articulate what we think is going on. And second, we're going to be able to use that to deduce why this could be going on, right? And graphs are going to help us do both things. Okay. So I'm not monitoring the chat, okay? So if there's something I should answer, you guys can punch me.
You're good so far.
Okay, thank you. So let's start with a brief recap of causal diagrams. So if you have never ever heard of causal diagrams before, the paper might be a little difficult to read because it assumes a little bit of familiarity, at least with the basic concepts of causal diagrams. But here in the talk, I'm not going to assume that much. If you are comfortable, it's a little easier. But I'm going to do a more extended recap in the talk here before we go into the examples. So what are causal diagrams? So causal diagrams have become a popular tool in the social and health sciences for explaining and resolving difficult problems in causal inference in a rigorous yet accessible manner. So when you see these graphs, just like nodes and arrows, you may say, oh, this is nice. It's like an interesting visualization. But it's more than that. It's actually a mathematical framework. And all the derivations we do there are formal derivations that we prove that this corresponds to certain mathematical derivations you would be doing the structure equation model, for example. So briefly, what causal diagrams provide is a parsimonious representation of the qualitative aspects of the data generating process that you're studying. So for example, when you draw a causal diagram like this, x pointing to y, z pointing to x, z pointing to y, this is saying that this variable z causes the variable x. This variable z also causes the variable y, and this variable x causes the variable y. So the letters here represent random variables. So for example, it could have x is a drug, z is an income, and y is health. The arrows denote a possible direct causal effect between one variable and the other. And no parametric assumptions need to be made regarding the functional form of the causal relationships, nor are the distribution of the random variables. Now, it doesn't mean that you shouldn't make parametric assumptions. You could if you want, but most of the results that we're going to discuss here do not require you to specify, is this drug affect health linearly? You don't need to specify that. Does income modify the effect of drug on health? You do not need to specify that. It's fully non-parametric. A priori, you're assuming that everything could be going on. This could be a fully non-linear equation, full of interactions and so on, okay? The same thing about the distribution of the random variables. We're not saying these are normal Gaussian random variables and so on. So far, we're being agnostic about this distribution. So it's just the most basic qualitative aspect of the data generating process is just saying what causes what, okay? And most importantly, what does not cause what? It's actually, this is the most important assumption in a causal diagram. It's the absence of errors, okay? So the assumptions here on this diagram is that, for example, Y does not cause Z. So that's one assumption we're making. Another assumption we're making is that there are no latent variables here that cause both Z and Y, okay? So the errors are not assumptions, the absence of errors are assumptions. And what are the building blocks of a causal diagram? So no matter how complicated a causal diagram is, so you can make a causal diagram with several variables, several different paths between these variables. It can be understood in terms of just basically three main forms of association. So these are the building blocks of any causal model we can have. And what are these three main sources of association? So the first one are what we're going to call, so I'm going to use causal language here. So we could discuss all this with graphical language, but I prefer to use causal language or more mechanistic language for these variables. I think it's more intuitive. So the first one is mediators. So for example, imagine you have a random variable X and a random variable Y. So a mediator is something that X affects Y because it affects this other variable Z. So here you can imagine, if I manipulate X, that changes the value of Z, that in its turn changes the value of Y, okay? So these are mediators. These are chains of this form, representing a causal diagram. Now, the other very common pattern is what we call common clauses. So that's when X and Y share a common clause. So this is also known as a confounder, let's say. So here I have a random variable X, a random variable Y. In this case, X does not cause Y, but they share a common cause Z. So Z causes both X and both Y. So this is what we call common cause. And the final main pattern of association, or main source of association, main building block of a causal diagram is common effects. So here we have again X, Y, Z, but Z plays a different role. So Z is neither a mediator from X and Y. Z is not a common cause of X and Y. So in this case, Z is a common effect. So I have a cause X that could cause Z and a cause Y that could cause Z. And they do not need to be related, but they share this common effect. So, for example, if you think there is a very easy example, even though maybe a unfortunate example, is death. So there are many things that could cause death, right? So you could have, for example, you can have an accident in the traffic. So that could be X, and that could be one possible cause of death. But you could also have a disease or something else. And these things need not be related at all, but they can share a common effect, right? So unrelated causes can share common effects. And this is also known as a collider because the arrows are colliding in this random variable, right? So you have the two arrowheads colliding. So that's why we can call this collider. This is going to be a language we're going to be using, this language of colliders. So now I want to go over each of these forms of associations, and we're going to discuss when information is flowing between one variable and the other, when it's not, okay? And this is the main thing to understand. If you understand this, then it's just a matter of practicing a little bit, and we're going to be able to solve any problem in deciding which variables we should adjust or not adjust and to identify a cause effect. So here, a mediator is X causally affects the random variable Y. So let's say that X is our treatment, Y is our outcome, and we have this random variable Z. So we say that Z is a mediator if X affects Y through Z. So the first thing to know is that this is a causal path from X to Y, right? Causal path in the following sense. If I manipulate X, this changes the value of Z, which in turn changes the value of Y. So this is part of the causal effect of X on Y. If we do not touch the random variable Z, you can imagine that this association is flowing. If I manipulate X, Z varies, then Y varies. Okay, so we have this flow of association unblocked, right? So if I don't adjust for Z, if I don't condition on Z, we're going to see that X and Y are associated in the data. On the other hand, if I condition on Z, so what do I mean by condition? So here condition, if it's a linear model, it could be including this on your regression equation, but more non-parametrically, condition on Z means just stratifying by Z. Okay? So it means that I'm subsetting the data into different levels of Z. So let's suppose Z is blood pressure. You could have high blood pressure, low blood pressure. I'm stratifying the data between high blood pressure, low blood pressure, and I'm looking at association between X and Y on each subset of my sample. So what happens if I have a mediator and I stratify the data or a condition or on the mediator Z? This blocks the flow of association, okay? So you can imagine water flowing. If I go there and I have this sequence, this chain of pipes, if I go there and I condition on the mediator, that's like closing the pipe and the water stops flowing, okay? So it blocks this flow of association between X and Y. So let's consider an example here. Imagine we have a drug X that affects an outcome Y. So for example, health, by lowering blood pressure. So that's the mechanism through which the drug works. So if I don't condition on anything and if I do a randomized controlled trial, for example, so I don't have any confounders, and I look between the association in drug and health, I'm going to see that there is an association. For example, the drug improves the health of the patient. But in this case, imagine we have no confounders, and then if you condition on blood pressure, you block the mechanism through which the drug affects health. You will not see any association between drug use and health status among those with the same level of blood pressure. So this is one first thing that you can see. If you want to measure the total effect of the drug, but you naively adjust for some of the paths through which the drug affects the outcome, you will be blocking perhaps unintended, this is unintended, one of the ways through which the causal effect goes. Right? So these are mediators. So now let's discuss common causes. So again, we have X and Y, share common cause Z. This is also known as a confounder or a backdoor path. Okay, so that's another language we can use, a graphical. So if we have a confounder or a common cause, if it's left on its own, this path of association is open and induces a non-causal association between X and Y. Okay, so remember, the first one is a causal association. This one is non-causal. So how does it look like? So as we saw, we have this pattern where we have a Z that causes X and Z causes Y. So when Z varies, both X and Y varies. So if we look at the data, we're going to see that X and Y are associated, but that's not because X is affecting Y or Y is affecting X. It's just because we have this common cause Z that affects both at the same time. So we have this association flowing, okay? So you can imagine this association flowing because of this association due to the common cause Z, of the confounder Z. And again, just like in the mediator case, if you condition on Z here, you block this flow of association. Now, in this case, blocking would be good because if this is a confounder, you want to isolate the causal association from the spurious association, right? So in this case, it would be a good idea. And if you want to have a visual image of what is going on, again, you could imagine water flowing through the pipes. If you go on Z and you condition, you're closing this pipe, and then you block the flow of the association between X and Y. Okay, so stratifying by Z blocks this flow of association. So again, so now let's go to the opera and mortality example. So suppose that, which is reasonable perhaps, that going to the opera does not affect mortality, okay, causally. It could, right? It could. We don't know, but I suppose it does. Let's suppose, however, that rich people, and then we're going to denote Z, for example, here, income, are both more likely to go to the opera and also more likely to be healthy. So this would induce, of course, an association between X and Y, right? So because your income is making you either go more or less to the opera, and then your income is also making you be more healthier or not, either because you have less stressful life or because you have better access to healthcare and so on. It doesn't matter how income affects that, but it could be affecting health. In this case, if we do adjust for Z, we do block this source of spurious association, right? So in this case, we want to adjust for income to block this spurious source of association. Now, of course, in the real world, we're not going to have only one confounder, but that doesn't matter, okay? Because once you understand these main sources of association, when we go to multiple variables and paths in the DAG, the logic will remain the same. Okay, so the logic will remain the same. So if you understand the basic principle, you can apply the logic to larger graphs. Now, our final pattern, like we said, are common effects. And then again, X and Y would share a common effect. And just like I told you before, just because two random variables have a common effect, so two causes can have a common cause effect, that doesn't mean they're associated. So the first thing to think here is that if you have something like this, X causes Z causes Y, and there are no other things between themselves, we should not see an association between X and Y, okay? So just because two things cause another thing, it doesn't mean they are related. They should be related. So you could imagine, again, just like if you want to have a visual, it's these two things collide on this node. And the association stops there. It doesn't flow between X and Y. They collide on this node. That's why we call it collider as well. But then, if you condition on this common effect, it's the opposite. What happens is the opposite from the other two sources, okay? So conditioning on this common effect opens this source of association and induces a non-causal association between X and Y. So now X and Y were not related, but if I look within straight of Z, this creates an association between X and Y. So this is unintuitive. I'm going to give you some more examples. But let's start. This is a very canonical example to explain this. So imagine, for example, that beauty and talent in a population of actors are independent, okay? They are independent. So nature randomly gives to everyone some beauty and some talent, and nature is not fair. You could be both very beautiful and very talented or not, okay? So it's not compensating. It doesn't have any compensating mechanism. So let's suppose that's how nature works. And now you go to the data, and let's suppose the movie agencies only hire actors whose beauty plus talent exceed a certain threshold. So they're saying both are important for having a blockbuster. I'm going to look at the person and I'm going to look both at their beauty and the talent. If their scores exceed a certain threshold, I'm going to hire them. So even though there is no causal or any other type of association at all between beauty and talent in the general population, you will see a negative association between beauty and talent, both among hired actors and non-hired actors. Okay? So if you stratify by this collider or this common effect Z, you will see this association and you will be puzzled, wondering, oh, what is happening here? And come up with all sorts of explanations. So again, like I said, since this is unintuitive, let's see an example via simulation, okay? So you can do this in R. So this is using the R language, if you're familiar with programming. You can do this yourself and see with your own eyes, that's what is happening, okay? So let's suppose that X is beauty, and this is a score, and let's say it's a normalized score. So this is a score between 0, sorry. It could be any number, but it's normalized in the sense that 0 is the average, and then if it's negative, you're below average. If it's positive, it's above average, and it has a normal distribution here. So you measure beauty and normalize it, and so on. Just like you do this with other scores too. And then let's suppose talent again. Somehow we were able to measure talent and we quantified that, and we also created a score. And again, it's a normalized score. 0 means you're average, positive means you're above average, negative means you're above average. And then let's suppose the hiring agencies do this very simple hiring criterion. So the movie agencies that if your beauty plus talent is above 0, if the sum is above 0, then you're hired, right? So what would you see in the data? So in the left-hand side, I'm showing you the plot between talent and beauty, and you see no association at all. So if you're more beautiful or less beautiful, it doesn't affect whether I'm going to believe you're more talented or less talented. However, if you look at the subpopulations, so here red would be the hired ones and blue the non-hired actors, you would see this negative association. So for example, you would see that If you're very talented, then it's less likely that you're very beautiful, or if you're very beautiful, then it's less likely that you're very talented, and so on. And why is that? That's what we call the explaining away effect. We have two potential causes for why you were hired. Either you could be beautiful or you could be very talented. And once I learned one of the causes, this makes the other cause less likely. So that's why learning the common effect of two competing causes creates an association between the two causes, even if they are not associated in the data. Does that make sense? So here you could think about all sorts of possible explanations. So maybe nature is fair and it distributes attributes in a way that compensates in one way and another. But this is a pure artifact of selection. Okay. So this is a pure artifact of how you see the data, like how the hiring process happens. So just to sum up, so we're going to go to the examples. So we have these three main building blocks. So we have mediators. So these are causal paths. If I don't condition a mediator, this is open. If I condition on the mediator, this is closed. We have common causes. These are called the confounders. These are non-causal paths. If I don't condition on the confounder, this path is open. If I condition the confounder, this path is closed. And we have common effects. These are colliders. These are, again, non-causal effects, non-causal paths, sorry. But the behavior, with your condition on Z or not, is the opposite of the other two. If I don't condition on a collider, this is closed. If I condition on a collider, we open this path. So if I condition a common effect, this open this path. And there's just one final rule to keep in mind to understand causal diagrams, is that if I control for the effects of a variable, this is equivalent to partially controlling for that variable. Importantly for us, if I condition on the effects of a mediator, this partially closes a causal path. And if I condition on the effects of a collider or the effects of a common effect, this partially opens a non-causal path. Okay? So now you should have all the tools to decide which variables to adjust for, to identify, for example, the total causal effect of X and Y. So we're going to be discussing here mostly total effect, but I'm going to make some remarks on direct effects as well. And why is that? Okay, so why is it? So the first thing to note here is that causal paths are paths consisting of sequence of mediators. So are only the directed paths. So these are the only causal paths, are paths that go from the treatment to the outcome on this direction. All the other paths are non-causal paths, okay? So then our task, if we want to estimate the effect of X and Y, our task is conceptually simple, right? At least conceptually. Doesn't mean in practice it is. You need to practice a little bit. But so first, so we want the total causal effect. So what I want to do, I want to isolate what I don't want. I want to block what I don't want. So I want to block all spurious paths from X to Y. And I don't want to perturb, I don't want to block any of the relevant causal paths. Okay? So all the directed paths, I want to leave them untouched. And all the other paths, which are not the directed paths, I want to block them. And that's the logic that we have. We want to block what we don't want. We want to leave untouched what we want. Okay. So this is the essence of the graphical condition known as the backdoor criterion or the adjustment criterion. And you can see the theorems if you want in the appendix of the paper. But the logic is basically this. And this will be our guiding principle to decide whether we should or not include a variable in a regression equation. Okay. So even though this is simple, mastering this does require some practice, okay? So what we're going to do here is apply those principles in very simple examples, okay? So any questions before we go to the examples? So now I'm just going to run through a bunch of examples and then...
Yeah, we had one question in the chat. I don't know if Grant, you want to read it out, and I'm happy to read it as well if you prefer.
I guess here.
I think you answered it, but it was more of because you talked about partially controlling for things being the same as controlling for them. I'm not sure I see it that way, but would like your reaction. Because I think if you condition on it perfectly, then at least you can recover the treatment effect if one correlation. Whereas if you do a bad job, you can never recover that from that model.
Yeah, so well, I don't know what I mean by poorly conditioning, but if you mean by I'm not conditioning on the bad control, but on effects of it, then
I guess if whatever you're in non-parametric world, but most people If you just took a simple average of the papers in the literature are not working in non-parametric ways. A bad parametric version of conditioning on a collider is worse than renders the result unusable. Whereas if you do condition on it perfectly, you can at least use that research to recover the actual causal effect. Is that a fair statement?
No, we do not want the condition of the collider, right?
Well, no, I know it's bad, but if you've done it, then, and you understand the correlation between the variable you actually care about and the collider, then you can recover the actual treatment pathway and the treatment effect. Whereas if you do a bad job and the relationship between Z and the actual outcome you care about is badly measured, you can never recover that, even if you know something about the relationship between X and Z.
I need to think about to see if this is true, because you would need probably more, you need a lot of information to undo the conditioning and recover the causal effect. So non-parametrically, basically would need a whole probability table of Z given X and Y, for example. So I don't know, yeah, but this would be, you would need assumptions about how they're related to do the unconditioning, let's say, and then recover the causal effect. And then if it's not parametric, this assumption is basically a joint probability distribution, conditional probability distribution, which may be difficult to specify.
Yeah. I guess if I'm going back to the simple example, if you fully understand the relationship between Z and Y, then you don't need to know anything about Y. You just need to understand the relationship between X and Z to map that through. Is, I guess, the intuition.
In a linear case, yes.
Even if it's not linear.
Yeah, but then the relationship is probably a full probability distribution.
But knowing the distribution of X to Z would let you perfectly recover the relationship between X and Y if you fully understood the relationship between Z and Y. And there was no third channel to get from X to Z. Or sorry, X to Y. Anyway, forget about it. It's fine. Okay. It's fine.
So now let's just practice. So what we're going to do here is, in all the models we're going to look now, our target of interest is going to be the average treatment effect of X and Y. So this is the treatment effect if I set the treatment to 1 versus if I set the treatment to 0. And I'm going to look at the outcome if I set the treatment to 1, and if I look at the outcome if I set the treatment to 0. So I'm using the potential outcome notation. So it's the average of the potential outcome if I set the treatment to 1 minus the potential outcome if I set the treatment to 0. There can be many different causal effects we're interested in. For example, it could be interested in direct effects, in indirect effects, and so on. And this changes a little bit of the discussion, because if I'm interested in a direct effect, and we're going to show you an example, you may want to condition on a mediator. But for now, we're just going to assume one of the most vanilla causal effect possible, which is the average treatment effect. It's the total effect of X and Y, meaning that I manipulate X, I see what happens to Y. Okay, if I could do a randomized controlled trial. So the observed variables are going to be denoted by black dots, and then observed variables by white empty circles. And the variable Z highlighted in red will be the variable whose inclusion it's going to be decided. So we're going to take this red variable and see, should I include this or should not include this in my regression equation? Now, we're going to use the simplifying language of good and bad control, okay? But in this sense, it should be useful for you to understand the logic, not just to memorize that this is good, this is bad. Because this is good, this is bad, depending on our goal, right? So it's always good and bad respect to what? It's always respect to some. So it's respect to achieving the goal that we want. So we're going to say it's good if it helps reducing bias, bad if it increases bias, and neutral if it doesn't matter. Either it doesn't do anything, right? It does not reduce nor increase bias. And for the last case, where we have neutral controls, I'm going to make brief remarks about how Z affects the precision of the estimate. Because most of the discussion above is for asymptotic, I'm going to make some brief remarks about the precision of the estimate in finite samples. So I told you guys, this is a little bit more than an hour, okay? So I saw when you put there. But if you want me to speed up, it's fine. So just let me know how I am in time, because this is not a traditional talk. It's more like a lecture, so it takes a little bit more.
I think you're fine. We might lose some people if they have to go to class or something at 11:30. Proceed.
Okay. And then I'm going to make some brief remarks about how it affects precision, in the sense that in finite data, I'm going to have a standard error, and then some variables may or may not help with reducing our standard errors. And the focus here is going to be practicing our graphical skills. And later, we're going to see how these very simple models can help make sense of real-world examples, such as the two paradoxes that I gave you in the first part of the lecture, which you may have forgotten already. Right? We had the two paradoxes there, the birth weight paradox and the antebellum puzzle. So let's start with some good controls. So these are easy cases. In our first model here, Z is a confounder. And like we just said, this is just like the example we saw. This creates a spurious association between X and Y, which are denoting by the red arrow here. And then once we control for Z, we block this source of spurious association, and we can estimate the average treatment effect, right? Unbiased of the treatment effect. So this is a good control. But now let's make it a little bit more complicated, but it's still the same logic. So here in models 2 and 3, we also have a confounding path, or what we call a backdoor path, due to this unobserved confounder U. Okay, so I have this latent confounder U. U causes Z and causes X, and U causes Y. So this creates this confounding path here between X and Y. Now, Z is not a confounder itself, right? So Z is not a traditional confounder. It's not a common cause of X and Y. So it's not a traditional confounder. But Z is a mediator of the confounder, right? So either it captures the effect of the confounder going through to the treatment, or captures, in the other model, it captures the effect of the confounder through the outcome. So we can still block this source of a spurious association by controlling for Z. Okay. Again, so whenever we condition on this middle variable here, we are blocking the source of association between U, Z, and X, or in the other case, between U, Z, and Y. So again, even though these are not, quote unquote, strictly speaking, Z is not the confounder of X and Y, it is on the pathway of the confounding path, and adjusting for Z blocks this confounding path. Okay, right. Now, it's usually useful to keep in mind that if I have any common cause between X and a mediator of X to the outcome of interest Y, this also confounds the effect of X and Y. Because sometimes you only think about confounders, you only think about immediate direct causes of your outcome and the treatment, the outcome. But this could be common causes in some intermediate path or some mechanism of the treatment to the outcome. So let's consider now these models here, model 4, model 5, and model 6. Should I adjust for Z or should not adjust for Z in this case? So these cases are the same thing as the models 1, 2, 3, okay? So if you consider, for example, model 4, Z causes X, Z causes M, and then M causes Y. So this is a confounding path from Z to Y, okay? And again, everything is open because I'm not conditioning anything yet. Model 5, the same thing. I have this confounder U that causes Z that then causes X, and then U causes M that causes Y. Again, I have this confounding path. U, Z, X, U, M, Y. And model 6, it's the same thing. And in all cases, just like in models 1, 2, 3, if I condition on Z here, I'm capturing this confounding path. So if I condition on, in the first case, I'm blocking the confounding path directly by the source of confounding. In the other two cases, I'm not blocking directly the source of confounding, but I'm capturing the confounding before it reaches either the treatment or the outcome, right? So in all these cases, adjusting for Z would block the confounding path. So these are good controls. Okay. Now, so this is a good and bad controls. Now we're going to encounter our first bad control. Okay. So in this example, I have this random variable here. No, so just notice that most times you don't know what the true DAG is. Okay. So it's not exactly that you are in this setup, but you can imagine these are tools that helps us think through. And even if you don't know the true DAG, that's fine. But you can write it down and then think about, oh, could this be happening or could this not be happening? So this variable Z is correlated with the treatment X. And why is Z correlated with the treatment X? Because I have this latent variable here, U1, causing both X and cause Z. So I'm going to see an association between Z and X. Z is correlated with the outcome Y. Again, so I have this random variable U2. U2 causes Z, U2 causes Y. So it creates an association between Z and Y. Z is pre-treatment, you could see here. So Z could be something that it's not affected by X. In this case, it's not. So if you think about it, this random variable Z is associated with X. The random variable Z is associated with Y. And then you say, oh, this random variable Z is not caused by X, so it's a pre-treatment variable. You think, wow, this is actually a confounder. I should adjust for Z. But what is happening here? So first note that there's no confounding between X and Y here. Okay, so there's no confounding between X and Y. So the path from X to Z here is blocked with the other path because Z is a collider. So again, just because U1 causes Z and U2 causes Z, it doesn't mean U1 and U2 are related and that you have association flowing from U1 to Y and U2 to X. So there is no confounding path here. And if I just run the regression of Y on X, this is actually an unbiased estimate. It would give me a valid estimate of the causal effect. However, if I condition on Z here, I open this path between U1 and U2 and the whole path from X to Y, this whole spurious path from X to Y. So then this is the first case where if I didn't adjust for anything, I would have the correct estimate. If I adjust for Z, I would have the incorrect estimate. And it could be even of the opposite sign, right? So you could have something that is positive. Remember, sometimes you don't know what the true DAG is. Then you adjust for Z, that it changes to be negative. And you say, oh, I'm glad I adjusted for Z because I would have reached the opposite conclusion. It turns out that you would actually be making the estimate worse rather than better. Okay. So this is the collider bias, or this is called M bias too because of this M structure that this graph can have if you put Z a little bit below, and it's our first bad control. Now let's see some neutral controls. So model 8 and model 9 here, we have that this random variable Z does not create nor block any backdoor paths, okay? So model 8, you could imagine this is a randomized controlled trial or randomized X. But of course, just because a randomized X, it doesn't mean that X is the only thing that causes the outcome Y. You can have other competing causes of Y that you either manipulate or not. This could be Z, for example. So there's no confounding, and we have this extra random variable Z, right? So should I adjust for it or not? So in terms of bias, I can tell you, it doesn't matter. If you're adjust for Z or it doesn't adjust for Z, it doesn't matter for identifying the causal effect. The same thing for model 9 here, even though we have Z that causes X, this Z does not cause Y except through X or other things. So it's not a confounder. There's no confounding. Whether you adjust or not adjust for Z is neutral in terms of bias. But these two random variables, it's not, they have different impacts on the precision of your estimate. And why is that? So imagine here, if I want to capture the signal between X and Y, right? So Y varies. So I want to manipulate X. X is going to vary, then Y is going to vary. And I want to isolate how much of this variation is because of a varied X and not something else varied. So if that's my goal, to get a better estimate of the signal, should I reduce or increase the variation of Y? Right? And then I'll let you think a little bit. And the answer is I should reduce, right? So if I want to capture what is the variation, the signal that I vary X, this varies Y, I want to reduce as much as possible other competing sources of variation of Y. So in the first model, adjusting for Z reduces the variation of Y. This helps increase the precision of the estimate. Now, on the other hand, if the same question, if I'm varying X, I'm seeing the variation of Y. To get a better estimate of the signal, do I want X to vary a lot or a little? And so imagine here, if I vary X just a little, is it going to be easier or harder to detect the signal of this variation causing Y? So the answer here is it's going to be harder. So for X, we want the opposite. We want X to vary as much as possible. Because the more variation causing X, the more chances we have to see variation in Y. So in the second model, adjusting for Z is going to reduce variation of the treatment X, and this is going to reduce the precision of the estimate. Okay. So as a general rule of thumb, in order to obtain more precise estimates of the average treatment effect, we want to reduce the variation of the outcome and not reduce the variation of the treatment itself. Okay. And in linear models, this is actually very easy to see. You just take the regression coefficient formula. What happens if you put one variable there? And then you're going to see that the residual variation where it enters the formula. And then you're going to see the variance inflation factor, for example, which is variation that Z explains of the treatment. And there's something else that I call the variance reduction factor, which is how much it explains variation of the outcome, right? So in the first model, Z improves the precision of the average treatment effect. In the second model, Z hurts the precision of the average treatment effect. But in both cases, you have an unbiased or consistent estimate of the average treatment effect. You're just going to get either higher or lower standard errors, okay? Now let's see another example of a bad control. So this is an example of bias amplification. So this is one of the few examples here that is parametric. So what I'm going to tell you here depends on some parametric assumptions. For example, linearity. So here we have again, Z is pretreatment. So this random variable Z is pretreatment. Z is associated with X causally. Z is associated with Y because Z causes X, that causes Y. And then you have the association. And also Z is actually associated with Y condition on X too. So if I condition on X, I have this association Z, X, U, Y because I'm conditional collider. So Z is also associated with condition X. So this seems like an ordinary confounder that is begging to be controlled, right? So like it checks all the boxes, pretreatment, causes X and everything. But no. So what happens here? So first we have this latent confounder, and without certain assumptions, we cannot identify the causal effect. So we have some bias here that we cannot remove. And if we condition on Z in this case, what happens is not only will fail to deconfound the effect, but it will amplify any existing bias. Okay. So in this case, Z is what we would call an instrumental variable. So you could use Z to estimate the causal effect, but not via adjustment. So it would be a different approach, which we're not going to discuss here. But if you naively put Z, for example, in your propensity score or in a regression equation, and you would imagine I could put Z in a propensity score, right? So it's Z is a cause of the treatment. Why not put in the propensity score? So if you put it in the propensity score or in a regression equation, doesn't matter how you do the conditioning. It could be just linear regression or non-parametric regression or so on. In many cases, it will amplify the bias that you already have in here. And the logic here is basically because when you adjust for Z, you're reducing the variation of X. And then what you're doing is you're reducing the signal that is causal and amplifying the signal that is not causal. So now let's see some bad controls. And this one are textbook examples of bad controls. So these are a little bit easier to avoid, even though you see all the time also happening in empirical practice. So if our target of inference is the average treatment effect, we want to leave, like we discussed, all channels through which the causal effect flows untouched. So if I wanted the total effect, the average treatment effect, I don't want a condition on things that lies on the pathway, the causal pathway from X to Y, because I'm going to be blocking this part of the very effect that I want to measure. So in the first example, model 11, Z is a mediator of the causal effect of X and Y. So if I control for Z, I'm going to block this very effect I'm going to measure, and I'm going to find no association between X and Y. So this is usually known as over-control bias, okay? So I have the causal effect flowing. If I condition on Z, it stops flowing. And then no wonder you're not going to find an effect of the treat because you controlled through the mechanism through which the effect happens. Now, this is the most obvious case, but there's no obvious ways where this can happen. And the no obvious way is, for example, not necessarily your conditioning on the mediator, but your conditioning on the effects of the mediator. So in the model 12, even though Z is not itself a causal effect of X and Y, Z is an effect of the mediator. So conditioning on Z is equivalent to partially conditioning on M. So it's not like you're going to completely eliminate the association between X and Y, but you're still going to bias the total effect estimate by conditioning on Z. Okay? Now, there is one caveat here. So here I'm assuming that you want the total effect. What if I want the direct effect? So I say, oh, no, but I actually want to know if X causes Y, not through Z. Okay, because I'm interested, maybe there are different competing mechanisms, and I want to condition on Z to see if there is an association that could be an alternative mechanism explaining the cause effect of X and Y. So that's mediation analysis, and there are many things that we could discuss. I'm just going to discuss some things about the control direct effect, for example. If you're interested in model 11, let's suppose you're in model 11, and we're interested in the control direct effect of X and Y, then adjusting for Z in model 11 would indeed be appropriate. Okay, so in the model 11 here. And then we would find that it's 0, which is the correct answer, saying yes, now Z fully mediates the effect of X and Y. But you need to be careful, and the reason is this. So let's suppose this is a randomized controlled trial. So if it's a randomized controlled trial, we manipulated the treatment X. Now, Just because you manipulated the treatment X, it doesn't mean, so X is unconfounded because you manipulated X. Just because you manipulated X, it doesn't mean that any effect, any mediating path from X is also unconfounded. Because, for example, let's suppose X is drug, you randomize who takes the drug and who doesn't take the drug. Z is blood pressure. You measure blood pressure, and then you measure the health outcome. Now, I want to know, does the drug affect the health outcome? Not through blood pressure, right? And you randomize the drug. You can estimate the total effect of X and Y, the effect of the drug. But you do not randomize blood pressure. Because, okay, the drug causes blood pressure, but since blood pressure is not randomized, other factors could be causing blood pressure, such as, for example, income. Maybe a person with higher income has either lower or higher blood pressure. Actually, I don't know what would the direction be. And a person with higher income or other socioeconomic factors also have higher or lower mortality. So this is a confounder U of both the Z, blood pressure, and Y. So even if you have a perfectly fine randomized controlled trial, if you adjust for the confounder here, you would be not getting the total effect, nor getting the direct effect. You would just getting a biased estimate that doesn't measure anything. So you would be concluding that, Z actually affects Y not through blood pressure, but no, this is just purely bias. And this is the colliding bias because X causes the mediator and the confounder also causes the mediator. And then you open this confounding effect, okay? So if you don't touch Z, it's fine. You're going to get the total effect of the drug on health. If you adjust for the mediator Z, if there is no confounding, you're fine, okay? But remember, you did not randomize Z. If there is confounding, then actually you could be reaching completely misleading conclusions about the direct effect and the indirect effect and so on. So that's it. So this is the only thing I'm going to talk about mediation. Okay? Now, again, let's talk about some neutral controls. So this is like the example we saw before, but a little different. So we have model 13. We're almost done, okay? Oh, so model 13, I have X causing this mediator M and mediator causing Y. And then I have this cause of the mediator. And then you would think, maybe if I adjust for the cause of the mediator, this is going to bias my estimate because I don't want to adjust for the mediator. But note, it's not a problem to adjust for causes of things, right? So the problem here is the effect of things. So if I adjust for the effect of a mediator, that's like adjusting for proxy of the mediator, a noisy version of the mediator. And this bias the estimate. But adjusting for the causes of mediator, it's fine. Not only it's fine, in this case, it helps improve the estimate in finite samples. So this is neutral. It doesn't matter if I adjust for Z or doesn't adjust for Z. But adjusting for this, for Z here, it's just like a model 8 in the other example that we showed, adjusting for cause of Y. So this reduces variation of Y, helps us get better estimates of the causal effect. And model 14 serves two purposes. The first one is that this is a post-treatment variable. So this is a cause of X. And in this example, adjusting for the cause of X does not bias the estimate. Adjusting for Z here does not induce any spurious association. However, it will reduce the variation of X, so we will reduce the precision of the estimate. In this example, adjusting for Z, even though you would not bias the estimate, you would inflate your standard errors unnecessarily, so it would not be advisable. But this is the first example where a post-treatment variable is not a bad control, okay, in that sense. And I'm going to show an example where it actually can help you. And this example is right now. So now let's just make the example a little bit more elaborate, and then adjusting for Z here is actually going to help you identify a causal effect of interest. So this is going to be our first good post-treatment variable. So the first thing here is imagine that we only have observation with W equals 1 recorded. So that can happen all the time. So for example, imagine you're studying the population of hired actors. Okay. So if you're studying the population of hired actors and you don't have data on the non-hired actors, you're already conditioning on a collider, whether you want it or not. The collider is there and you're conditioning implicitly on this random variable. So imagine this is the case here. So for some reason, maybe W could be your hospitalized and you're just looking at hospitalized data of patients in the hospital. So you have only data with W equal 1 recorded. So what happens here? So again, this is a collider. If I condition on W, this opens this path. So I open this non-causal path, XCW UI. So now, even though there is no confounding between X and Y, because I'm looking at this data set, which is conditioning on W equals 1, I'm going to have this source of spurious association between X and Y. Am I hopeless? Turns out that in this example, you're not hopeless. And actually, a post-treatment variable would help you. Okay, so this depends on you believing this causal diagram. Okay, but it's just help us thinking through. So note that if I further adjust for Z here, I block the colliding path. So if I further adjust for Z, I block this colliding path. So then this biased path is blocked. So this would allow us to estimate the average treatment effect for those in my sample. Okay, so it's not the average treatment effect the whole population because I don't have data on the whole population. I just have the data on those that are recorded, or W equals unrecorded. So just data on hospitalized or data on hired actors and so on. But I could estimate the average treatment effect for those people if I adjust for Z here. And it turns out actually in linear models, we could fully recover the average treatment effect. But of course, it's because in linear models, there is no effect modification. And the effect on those on my sample is the same as the effect on the whole population. So there's no magic, right? So that's why in linear models, we'll be able to estimate the full average treatment effect. But even non-parametrically, you can estimate the average treatment effect of those in my sample. And you would be conditioning on a post-treatment variable. And in this case, the post-treatment variable would be then a good control, right? So this is another counterexample to the common folklore. Not the only one, okay? There are more counterexamples, but I'm going to show you much more. Now we're almost done. It's like almost the final examples here. So these are vanilla cases of bad control. This is usually called selection bias in epidemiology, not to confuse with selection bias from economists, because economists call confounding bias selection bias. So here, contrary to other model, controlling for Z is not harmless anymore. In model 16, controlling for Z actually opens the colliding path. So this creates again collider bias or selection bias. And in model 17, the same thing. We open the colliding path, but not only that, we also will open another biasing path, which cannot be seen on the graph, which leads to the last example here, which is what we call case control bias. So now this is the last example. So this one is the one that it's just a little more challenging to see why this happens. So here we have the effects of the outcome. And controlling for effects of the outcome is rarely good, okay? I'm yet to see an example where it would be good. So usually that's a very good rule of thumb that you should never ever control for the effects of the outcome. In our last example here, Z is not in the causal pathway from X to Y, okay? And Z is not a direct cause of X, and Z is connected to Y. So you may think, so like model 8, controlling for Z is harmless because I cannot really see that if I condition on Z, I'm opening any path. And perhaps it's even beneficial for precision, okay? But controlling for the effects of the outcome induces bias even without any error from X to Z directly, okay? And this is a bad control. And the reason here is that because when we represent causal diagrams, we usually omit the error term, the independent error term. And that's why we cannot see that there is a problem here, but there is a problem here. So if we put the error terms explicitly, then we see that if I condition on Z, I create an association between X and the error term of Y. Okay, because Z is a collider. Sorry, Z is the descendant of a collider, which is Y itself. So I create this spurious association between X and the error term of Y. So using econometrics language, now X would be endogenous, even if it was not before. Or if you want to use potential outcomes to see that, you can also draw the potential outcome, Y sub X. And you can see that conditioning on Z creates an association between X and Y sub X. So conditional ignorability also does not. Okay, so this is a little bit more advanced. This is the only case where if you want to really see with your own eyes the spurious association happening, you need to expand the diagram a little bit to see that happen. Okay, so now just to conclude, going back to birth weight paradox. So if you remember, the paradox was the infant born to smokers. Okay, so just before saying that, so we saw these very simple examples, right? Real life is more complicated than that. And then some people say, but I never know what the DAG is. And that's okay. You can still use the DAG to postulate mechanisms and see ask what if questions, right? What if this was happening? Should I adjust that or should not adjust that? What if was this happening? And also explain some unintuitive things on your data set. So it can guide you to think through problems, right? Even if you're not fully confident. And then you can do sensitivity analysis as well. which I can give you another talk some other day if you guys want, because that's actually one of my main areas of research. What happens if you cannot identify the causal effect, or you don't know the causal lag, and you have unmeasured confounding, for example. But now let's see how these simple tools can already help us solve these paradoxes. So we had the paradox again. If I look at low birth weight infants, it seems that smoking is beneficial. Does that mean that smoking is indeed beneficial for low birth weight infants? And the answer is no. And there is a simple causal diagram that we saw there that could explain this reversal of association. So imagine here that X is maternal smoking, Y is infant mortality, and Z is birth weight. Okay. And imagine U is unobserved risk factor, such as other birth defects or malnutrition, that could also affect birth weight. Now, here being charitable, we're saying, imagine that X is not even confounded itself, right? There's no other unobserved confounding. Could we still see this reversal of association in this very charitable interpretation of the data set? And the answer is yes. So notice here that if you condition on Z, we create this collider bias. And what is happening here? When I'm stratifying by birth weight, I would be inducing a spurious association between smoking and mortality due to competing risk factors. And the reason is low birth weight can be caused either because of smoking or because of other defects, right? Or other causes like malnutrition or birth defects. So if I learn that a mother smokes, and I learned that, if I learn that the mother does not smoke, and I learned that the child has low birth weight, then it must be that this low birth weight is explained by something else, right? That could be the birth defect or malnutrition. And this something else could be an even more serious cause of mortality. And that would induce this spurious association as before. So this is the same example of beauty and talent, right? When I condition on low birth weight, I'm explaining away one source of controlling for a common effect. And once I learn about the source of one common effect, this could explain away the other thing. What about the antebellum puzzle? So that's the same idea. So does it mean that nutrition reduces the height of adult men? There is also possible explanations for this paradoxical finding without appealing to any crazy theories. And the reason is this. So this is another case where we are conditioning without knowing. So in fact, these records that people use to compute average height is not from the whole population. It's not a census. This is data from individuals enlisted in the military or in prison, which could be equivalent to conditioning a collider. So you could imagine that Z is either you were in the military or Z is in prison, Z equals 1. And we have data in our data set, Z is always equals to 1. We never see the Z equals to 0. And let's consider the case of prison records. And X be childhood nutrition, Y adult height, and Z an indicator variable for whether you were arrested or not. And it's not very difficult to argue that both childhood nutrition and height, because it's well known, at least in the past, that height predicts economic performance in one way or another. Now, probably more or less, that we have technology and so on. But so one could argue that childhood nutrition and adult height, at least back then, could have pathways to committing crimes through socioeconomic opportunities, and that could lead to selection bias. So this is just one possible mechanism through which you could see this reversal of association happen. You don't need to come up with elaborate causal theories. So this is another example, which is useful for randomized controlled trials. Jeff Wooldridge, I don't know if you're familiar with him, is a famous econometrician, has a famous econometrics textbook, which is widely used in economics, both graduate and undergraduate. And so here he's asking on Twitter, suppose I have two fourth grade test scores, math 4 and read 4. I want to estimate the causal effect of class size on performance. So does class size increase or class size, increase performance, and so on. Now, she's saying, assume I have convincing controls. Now, instead of assuming I have convincing controls, assume I did a randomized control trial. I randomized class size. I want to measure performance. So is there a way to use a DAG to illustrate why I should not include read 4 on the equation for math 4? So why I should not include the reading scores in my regression for math scores? And it's again, you can see, we saw this example again. It's the same model we saw there before, why we should not. So imagine here we have X is class size, okay? And we're randomized class size. So there's no confounder of class size. Y is math scores, Z is reading scores. And they were measured after randomized, okay? So after I did the randomization. And I have this latent variable U that is the student ability. And if you agree with me, the student ability would predict both reading scores and math scores, right? Because if the student is good, probably he's going to get good scores regardless of class size, both in reading and math. If the student is bad, probably going to get bad scores in both. And then you did the randomized trial, you ran the regression of Y on reading on class size, and then you say, but maybe, and then let's suppose the estimates are a little noisy, and say, oh, maybe I should control for reading scores, because reading scores would be a proxy for intelligence or something else, and I'm gonna get more precise estimates. So let me include reading scores. So now you would have ruined a completely perfect, unbiased estimate of your randomized control trial. Because once you condition on Z, what happens here is that you open this colliding path X, Z, U, Y, and you bias the effect of class size on math scores, and vice versa, right? So if you want to estimate the class size on reading scores, you don't want to control for math scores. What if these were scores before the randomization? Then that would be fine, okay? If these were scores before the randomization, that would be fine. And what about multiple controls? When considering multiple controls, the status of a single control as good or bad, because we're just seeing one example, 1Z, may change depending on the context of the other variables, but the main lessons remain, okay? So everything we discussed remain. You just consider collectively the controls as a set. So a set of variables Z would be good if the set blocks all non-causal paths from the treatment to the outcome. The set leaves any mediating paths from the treatment to the outcome untouched, and it does not open any new spurious paths between the treatment and the outcome. Okay, so the same logic as before, but now you look the whole set. And here I say, but what about efficiency? Same logic again. We should give preferences to those variables closer to the outcome than those variables closer to the treatment. So this is just a rule of thumb, okay? There are more formal criteria for that. So long, of course, this does not spy identification, right? So you're not including anything that, or excluding anything that hinders identification. Now, if you have a bunch of variables, it's going to be hard to do this by hand, right? But you do not need to do this by hand. There's open source software with efficient procedures to do this for you. But I still think it's very helpful for you to understand this, because you can understand the output of the software, right? Just accept. You can have a critical assessment of what it's doing, especially to know, did I draw this DAG correctly? Why is it that it's not saying for me to adjust this or that and so on? But you can draw DAG, and the software can help you identify that. So there's this challenge, and for the sake of time, I'm going to skip. Yes.
Yes, Carlos, there's a question in the chat.
Okay.
Right. It's me again. You made that throwaway comment where you said that controlling for a pre-treatment reading score in the math equation would be okay. Would that not reduce the precision of your estimate of the treatment effect? Can you go back to the...
No, because in the randomized control trial case, no, right? So if you randomized X, nothing causes X. So the pre-treatment reading score could not be causing X because you randomized it. The only thing that the pre-treatment reading score could be associated with is with the outcome. Okay. And very likely it would be associated with the outcome, because if the student, you imagine you have this common latent variable, which is a student own ability or whatever, right? And most likely the student ability didn't change a lot from before the randomization, after randomization. The reading score could be a good proxy for the student ability. The same graph we have here, but without the error from X to Z, okay? And then that would be good for precision. Most likely good. We cannot know for sure, right? Because this is a statement that is asymptotic. It's not like finite, like exact finite sample state.
Yeah. Okay.
It's the asymptotic variance. So even though it's finite samples, I'm saying it's finite samples, but it's still it's asymptotic precision, right? But yeah, so usually it would be kosher. It would be safe, okay? So if you have pre-treatment scores, that would be kosher to put them on your regression for a randomized control trial in this case. Right? And then in case in the DAG, by just deleting the XZ arrow. You would be deleting the XZ arrow. Then you have Z is connected to I. I say, maybe it's going to be good for precision and it doesn't hurt my estimate. Now, there's this example here, which I'm not going to discuss just for the sake of time. But the point here is this is another example where controlling for post-treatment variables is good. So just another counterexample. And here, the interest would be a little more complicated. I want the joint effect of X1 and X2 on Y. And then if you just think about it a little bit, you would see that I actually want to adjust for both Z1 and Z2 to block all the spurious paths. Okay. And oh, but you're controlling for a mediator. Why can you do that here? And the reason is if I'm intervening both on X1, X2, the causal path from X1 through X2 doesn't matter anymore because I'm also intervening on X2. So that's why it's kosher to condition on these mediators, X1, X2. If you want the total effect of X1, then no, right? But this would be the joint effect of X1, X2. So there's more to the world than total effects, right? You can have joint effects, you can have direct effects and so on. That's the whole another lecture too. And then finally, just to say, we can also do sensitivity analysis, but I didn't put it here. If you have unmeasured confounding, what can you do? You don't need to give up. You can still conduct your investigation, but then you need to be honest about the possibility of unmeasured confounding and just do some sensitivity analysis and then report honestly how much unmeasured confounding would be required to overturn the results, right? Just to conclude, so we have seen through several examples, and sorry for running over all the time, but this is a hard lecture to give in just 50 minutes. So we have seen through several illustrative examples how simple graphical criteria can use to be decided whether a variable should or should not be included in a regression equation and whether it can be deemed a good or bad control. Many of these examples act as cautionary notes against prevailing practice. So for example, not all pre-treatment variables are good control. Not all post-treatment variables are bad controls, and some may even be necessary for identification. In all cases, you need to have knowledge about what you're studying, right? So you need to understand, as a scientist, you need to understand the topic you're studying because we need to have structural knowledge. Like what causes, what doesn't cause, what are the possible competing explanations, like confounders and so on. And this knowledge is indispensable for deciding whether variables are good or bad control. It doesn't matter if it's a DAG or not. Okay, you could represent this knowledge in other ways. But what I showed here is that graphical models provides a natural language for articulating this knowledge. So you can imagine, I truly believe in this. This is what if questions, like what if the world was this? What should I do? At some point, you need to commit with a model, a working model. But I'm saying in the beginning, you can explore there, and then you commit to a working model. Then explore violations of the model or variations of the model. The graphical models provide a natural language for articulating this knowledge, but not only that, it also is an efficient tool for examining the logical ramifications of the knowledge. So everything we're concluding here, when I show you the DAG, is just a logical ramification of saying, what if the world was this? Should I do that? And then it's saying, yes, you should, or no, you should not, right? And then if you postulate different assumptions, the conclusions will be different, right? So each DAG can lead to a different answer. And that's it. Thank you. And you can find all of this on my website. And then I would suggest maybe now it would be easier to read the paper, and also suggest reading the appendix, which there are some technical discussions in the appendix, which I didn't over here. And then from here, so this paper is actually cites lots of references where these results. So it's like this, it's distilling all these results on more technical references. Then you can follow up on the technical references too. And maybe it's going to be easier to also read the technical references. Okay, so thank you. And that's all I had for today.
Thank you so much, Carlos, for this really insightful talk. And thank you, everyone, for joining us this morning. If you have any other questions, you can email us at talktospark@mcmaster.ca. And we also have a really quick feedback survey, which, thank you, and yeah, you posted in the chat. So please take a minute to fill it out. And you can visit our website for upcoming events as well. Thank you, Carlos, again. This is really great.
Thank you. It was a pleasure to be here. Thank you all.